Welcome back once again. We are still on covalent bonding, and under covalent bonding, having gone through almost all the types of bonds and the concept that we need to know under bonding, we are talking about a theory or a concept that says that no ionic bond can be 100% ionic, or no covalent bond can be 100% covalent. That is what this topic seems to explain. Continuity of bond types. It simply says that covalent bond or ionic bond may have some other type of bond formation or characteristics in that particular bond. We have looked at the first scenario or the first case for ionic bonds or compounds. The theory here just said that cations have polarizing power and they polarize the anion. Anions are polarizable, and so when they are polarized, this introduces some covalency into the ionic bond, and so no ion bond can be 100% ionic. We saw that if the charge density is high, charge density simply means charge over size, or we say E over size. Charge density is high. This ratio will be high if the charge is high and the size is small, or if the charge is constant and the size is small, then of course charge density will be higher. The higher the charge density, the greater the polarization of the ionic bond and the less ionic that compound becomes. So in summary, we saw that, or we discussed that going across a period, ionic characteristics decreases. Ionic character decreases or decrease. Why? Because charge or E over size increase. As the charge density increase, so polarizing power increases. Going down a group, we said that ionic character increase. In going down a group, ionic character increase. Why? It is so because charge over size decrease. Therefore, polarization down the group decreases if we have the same charge. That was what we discussed in the last video on ionic compounds. So today we are going to look at, in this video, we are going to look at the second scenario where you have a covalent bond, heteronuclear covalent bond. So hetero a typical example is say HCl. What happens? In HCl, this bond we say it is polar covalent. It is polar covalent in the sense that because the two atoms that are sharing the electron pair are not the same, they have differences in electronegativity. And so the more electronegative atom, which is chlorine in this case, will draw the electrons more onto itself than the hydrogen. When this happens, we have a permanent dipole. In other words, we have a permanent separation of charges. This becomes negatively charged, and that becomes partially positively charged. This polarity here is established in the compound permanently. Now, when this happens, once the charges are separated, the bond or the electron pair that is supposed to be shared equally amongst them is shifted onto one than the other. This introduces some ionic characteristics into it because of the charges. The separation of the charges introduces some ionic characteristics into the covalent bond. And so at all times, this covalent bond here can never be 100% covalent because of the separation of charges. Some electrostatic force of attraction will be introduced in there, and we say the bond is not 100% covalent all the time. This bond can never be 100% covalent because of the separation of charges or separation of electron clouds. Even the third scenario, where we have homonuclear, diatomic bond like hydrogen to hydrogen, or chlorine, or oxygen. In other words, oxygen like this, or even nitrogen. In any of these homonuclear diatomic molecules, in covalent bond, we say they are pure covalent bonding, or they are pure covalent bond. We call them pure covalent bond in the sense that the two atoms sharing the electrons are equal, and therefore they have equal electronegativity. So we expect that at all times, the electrons being shared, the electron pair or the electron cloud, will remain in the center of the bond, or will remain equally on each of the atoms. If that is the case, then of course the bond can be said to be 100% covalent. But unfortunately, Van der Waal explains that electrons are mobile. They are not stationary, and so as they move, there will come a time that within a fraction of a second, this electron pair can be shifted onto this hydrogen atom here more than on the left hydrogen atom. At that instant, this hydrogen atom will gain a very small negative charge, and this atom will gain a very small positive charge. Now, this separation of charges is assumed, and so we say it is induced. It happens within a twinkle of an eye or a fraction of a second. And at that instant, if there's a similar molecule to this one here, that molecule can also be influenced or be induced to become polar in that same manner. If it becomes polar in that same manner, this one will also become partially positive charge, and this become partially negative charge. So at the instant where there is this separation of charges, or there is this electron cloud being shifted onto one atom than the other, the molecule, which is called a pure covalent bond, ceases to be a pure covalent bond. And at that instant, we say that some ionic character is introduced into it. So this is what Van der Waal uses in explaining the intermolecular forces that exist between such molecules. When we come there, I'll use the same principle to explain it. So continuity of bond types is just telling us that no bond can be 100% ionic or 100% covalent. And the reasons that we assign to it are: one, you take the ionic bond and explain the fact that polarization of the whole compound ionic structure by the cation brings in some ionic characteristics, brings in some covalent characteristics, such that you have a compound which is ionic, but then it will not be 100% ionic. Or you may have ionic compounds, but some behave more ionic than the others. Why? Because in those that do not behave as very pure ionic compounds, polarization in there is high, and therefore covalency comes in. When you take a electronuclear diatomic molecule like ACl or HF, water, any of them, they are different atoms, and so have different electronegativities. So at all times, this one, they have a permanent dipole, because at all times the electron cloud or electron pair will be shifted more onto the most electronegative atom than the other. And so that permanent dipole brings in some ionic characteristics, because there will be some kind of electrostatic force of attraction in there. So all such polar compounds or molecules cannot be 100% covalent. In homonuclear diatomic molecules, we expect that to be 100% covalent, but even that, Van der Waal explains that at certain times they are not, because as the electrons move, there's a probability that at one point in time all the electrons will be shifted onto one atom, at which time that particular atom becomes negatively charged and other atom becomes positively charged. And when this happens, there is that temporal polarity. And so if it's a similar molecule close to it and there's the same polarity, they can attract each other by some kind of electrostatic force of attraction. Like this hydrogen here, if it becomes polar at that instant, and this hydrogen molecule is also close, and it also becomes polar the same way, a force of attraction can occur between this negative charge and that positive charge. And that force Van der Waal, or chemists named after Van der Waal, they call it weak Van der Waal forces. That force of attraction is a very weak, we use the word very to describe the weak, a very weak electrostatic force of attraction. And that is the major force, intermolecular force between all non-polar molecules. That is a major intermolecular force between all nonpolar molecules. That weak electrostatic force, we call it the van der Waals forces. Van der Waals forces. Or more appropriately, we call it induced dipole interactions. Induced dipole interactions. We will introduce to it. So that is it. That is the topic. Now, this theory is purely explained by use of electronegativity factors or electronegativity figures. So, if we have two atoms given with their electronegativities known, you can tell, chemists have been able to determine by just looking at those figures and find the difference between them to determine whether they form an ionic compound or they form what? A covalent compound. So we have a subtitle called electronegativity and bond types. This is what chemists have established. If the difference in electronegativity between two atoms that are trying to form a bond is very small, very small, say from 0 to about 0.4, it will determine that they form a pure covalent compound, pure covalent bond. If the difference, I call this figure here, change in electronegativity. So delta En. Electronegativity is represented by En. So if I put the symbol change here, it means that the difference in electronegativity. So if the difference in electronegativity between an atom A and another atom B forming a bond, if you know the electronegativity figure for this and know the electronegativity figure for this, and do the subtraction, the difference between them, it falls within this small figure. Chemists have so determined that they can form a covalent bond, and that may be nonpolar because the difference is not so much. It means that almost all the time the electron pair may be equally shared between the two because of the fact that their electronegativities are not so different. If the difference is between 0.4 to say 1.8, you get polar covalent bond. And if the difference is above 1.8, okay, if it is greater than 1.8, then you get ionic compound. You get ionic compound. So that is the theory here. Here, the electronegativities of the two atoms are so close, so they form a pure covalent bond, telling us that the electron pair or electron cloud will almost all the time be shared equally among the two atoms. Here the difference is big. From 0.4 to 1.8, the difference is big. So it will form a permanent dipole. I mean, there will be a permanent polarity between the two atoms forming the bond, the two atoms A and B forming the bond. There will be a permanent dipole. One will be the negative, and then the next one will be the positive. And so that will be a polar covalent molecule. And if the difference is above 1.8, that is anything above 1.8 to about say 3 thereabout, they form an ionic compound. Here, the difference is so much that if it tries to form a covalent bond, after donating, after donating the electron, it can stay on its own. The other atom B here, the other atom B will be so electronegative that it will accept the electron and keep it. And the first atom will have low ionization energy and low electronegativity, so it can conveniently donate the electron, and that will be free. So that is the theory we use. Questions will come on all this. After looking at all this theory, we are going to take time to look at questions, and we see that all the things that we are studying, when it comes to bonding, questions are asked such that even in A, I and II, even in A, I and II may come from different types of bonding. That is why so far we have been looking at only the concept or the theory surrounding bonding. But we have not tackled any question. We'll solve almost all the questions.